Hello, hello. Oh, there I am. I am going to start the lecture. So if anyone is still writing, you may want to mute this so that way you're not distracted. I will respond to you over text if it's not too distracting from the lecture if you have questions, but I will be focusing on the lecture now. Um, for the people who have taken it without giving away any of the questions, um, how was it? Good. It was good. It was good. Seemed fine. Wasn't too easy, wasn't too hard. Okay, that's what I was aiming for. Um, yeah, there was a couple people got one version that didn't save that had set law proof that couldn't be done. Um, if you got that one, you were compensated for it. I think it was just two people. So if you got one that was insanely difficult, yeah, that wasn't your fault. It literally couldn't be done. So I left a comment on yours and you were compensated for that. So that was my apologies. That was uh, half my fault, half Canvas's fault. I saved it. Canvas didn't save it. I didn't double check in time. Um, okay. So today we're going to finish up propositional logic and then we're just going to call it a day. So we're not going to move on to the next lecture today just because you did a test. So I'm going to start off by talking a little bit, give you a break from doing work, and then we'll do the practice questions from last time at the end. And yeah, so what's kind of nice about today is that the stuff that we're talking about is stuff that you've already done. We're just going to give names to stuff that you're already familiar with. So it's not that much extra work. Um, Basically, you've done some truth tables already. And when you have a truth table, you have a bunch of ones and zeros in your final column. You have this complex, well formed formula, and it's true in some cases, false in others, typically. But sometimes you have well formed formulas that are always true, and you have well formed formulas that are always false. And sometimes there's well formed formulas that are true sometimes and false in other times. And each of those have different names. So there's three types. The first type at the top, we have well-formed formulas that are called tautologies. So here's the IPA for that. Tautology. Tautology. So uh, we use a capital T. Well, it's not really a capital T. It's like a long T. So we can actually use these in propositional logic formulas. So we can do something like P or long T or P or we call this top or tautology. And this is basically a formula that is always true. So no matter what scenario you're in, this will always be true. So one example of a well-formed formula that is always true is something like P or not P. So I can show you a truth table for this. So if you set up a truth table for P, so one situation it'll be true, another situation it'll be false, and we set up not P for that. So this is the case where we flip it. If P is true, not P is false. If P is false, not P is true. And then we say, what happens if we take P or not P? Well, if we remember the conditions for or, well, P or not P is true if just at least one of those is true. So in the first row, well, P is true, so P or not P will be true. And in the second row, not P is true, so P or not P will be true. Because every single row is true, we say this is a tautology. So this is a case that will always be true. And we can think of English sentences where this is the case. Um, like I want to go outside or I don't want to go outside. Uh, It'll be a good thing or it won't be a good thing. Uh, your partner's good for you or your partner's not good for you. Well, these are sayings that are completely useless in real life because they're always true sayings, but we say them a lot. So these are things that will always be true. Contradictions are things that we're already familiar with. We talked about them in the first week, and we have these in logic as well. And with contradictions, we use the upside down T. We call this bot. We call this the falsum. It's just up, but upside down. And we can use this as a symbol as well in logic. So basically, this is where every entry, every row in our final column in our truth table is going to be false. So this is a case of P and not P. That would be one example. So the same truth table we can set up. So P 1, 0, not P would be 0 and 1. And remember, for P and not P to be true, uh, or for the and to be true, both things on each side have to be true. Well, in the first row, if P is true, then not P is false. So both of these are not true. P and not P will be false. In the second row, well, P is false. Therefore, P and not P will be false. So if we take a look at all of the rows of P and not P, well, they're all false. Therefore, we have a contradiction. And contradictions are things that we're a lot more familiar with linguistically. Like the sky is blue and the sky is not blue. I have a dog and I don't have a dog. My floors are carpeted and my floors are not carpeted. These are things that both cannot be true and false at the same time, or things that, oh, well, the sentence cannot be true because uh, one part is directly contradicting the other. And in a truth table, this just means in every possible situation, the outcome cannot be true. So each of these are just one example. So P or not P, P and not P. These are just one examples of tautologies and one example of contradictions. But as we go through complex well-formed formulas and we build truth tables, we find a lot more examples of well-formed formulas that can be contradictions, that can be tautologies. Um, but the majority of well-formed formulas that you find are what are called contingent well-formed formulas. And contingent might not be a word that we use every day in real life, but contingent does mean what it means colloquially. That means that the well-formed formula, the truth of the well-formed formula, is contingent on the truth of its parts. So, for example, here's just a regular truth table for P or Q. Well, we don't have to go through this line by line, but we know that it's going to be false in the final row when both when both P is false and Q is false. So when we say it's contingent here, it's contingent on the values of P and Q. So it is true in some rows and it's false in other rows. So because there's a mix of ones and zeros, we say this is a contingent well-formed formula. So contingent basically covers everything that's not a tautology and not a contradiction. So yeah, a conjunction is contingent. Basically all of the regular operators we saw, like if we have not P, um, so this column for not P is contingent. Q on its own is contingent. P and Q is contingent because P and Q would give us 1, 0, 0, 0. The conditional is contingent. Yeah, pretty much all of the operators except for the tautology and the contradiction itself would be contingent. So yeah, so these are the three terms that are uh, what you're being asked to use for that third question on the third assignment. You're asked, is it a tautology, a contradiction, or contingent, and prove it with a truth table. Basically, you set up the truth table first, and that's how you answer it. But the more problems you do, and if you've taken a lot of logic courses, you may actually be able to just look at a formula and tell if it's a tautology, a contradiction, or contingent first, and then prove it. So eventually, you actually develop some sort of intuition with these formulas. And it's kind of scary when you get to that point. Um, but it's kind of neat in a way. So we do see a link, contradiction with semantic inferences, like what we learned in that first week with logic. And we're about to see another connection here. But before that next connection, I just want to double check. Are there any questions about these three terms before we move on?
So we don't have any symbols for contingent, right?
No, there's no specific symbol for contingent. We have specific symbols for tautology and contradiction because they're static. They're the same all the time. Contradiction is always just zeros, and tautology is always just ones. But contingent can be any combination of ones and zeros. Okay, so I mean it's kind of perfect because you just did a test on semantic inferences. So uh, entailment actually shows up in logic as well. So we worked with something called the conditional operator, and entailment can actually be represented and discovered using the conditional operator. So uh, to remind you, and you really don't need reminding at this point because you just worked with this and you just went over this. But if A entails B, the idea was that if A is true, then B must be true. And if you think about the conditional operator, this is like saying that if you have a one and an arrow, then if you want the relationship to hold, you have to have a one here. And if you think about this in terms of logic, uh, if the conditional is going to be true, if you have a case like this, then what does this output? This outputs false. And that would be like saying that there's no entailment. If you have one arrow zero, it's false. That's like saying there's no entailment. So we can use the conditional to check for entailment. So I can show you how we can do this. Oh, sorry, I'll keep this line up. Okay, so let's say we have two well-formed formulas, alpha and beta. And we want to ask ourselves, does alpha entail beta, or just does A entail B? It's the same thing. We're just changing A to alpha and B to beta. That's really all we're doing here. To check for entailment, we just have to ask ourselves, is alpha arrow beta a tautology? In other words, if alpha is true, then does beta have to be true? So in terms of a truth table, we're just setting up a truth table such that in the end, we have alpha arrow beta, and we just need to check to see if all of those rows are one in the end. And that's because in the end, what we're really checking to see is that we don't have any cases where we have one arrow zero. So we don't want this case because then no entailment. So this is how we can use logic to check for entailment. So let me just move that away. And we can use this specific example here. So I already have the truth table set out, so I just want to talk through this. But the example here is to show that P and P arrow Q entails Q. So really the difficult part about this isn't the truth tables at this point. You can do the truth tables at this point. It's just the same setup as before. It's the same process as before. The difficult part is just setting it up and saying, we have an entailment. We have to show what's the setup. That's the tough part. So if we want to show entailment, we're asking ourselves, does this part, does alpha entail beta? So we need to turn this into a formula where we have alpha arrow beta, and we need to show that these will have all ones in the end. So that's what we've done in this. We've basically taken our alpha here, P and P arrow Q. We've put an arrow. We've taken our beta here. And we're just going to show with the truth table in this row here that they're all ones in the end. So when we build it up piece by piece, we've made our columns for P and Q. We've done the truth table for P arrow Q. So this is what you're familiar with already just from the basic truth tables. And then at this point, P and P arrow Q, it gets a little bit more complicated. So at this point, we're comparing these two rows. It's going to be true when both P is true and P arrow Q is true. So it's true in the first row because P is true and P arrow Q is true, but it'll be false in the rest because in the second row, P arrow Q is false. Therefore, they're both not true. And in the third and fourth row, P is false. So P and P arrow Q is false. But then in this last row, we're going from P and P arrow Q over to Q. So if we just draw the little arrows in, we have one arrow one, and then in the second, third, and fourth rows, we're going to have 0 arrow something. And if we just remember the conditional again, if you have 0 arrow anything, then it comes out to true with the conditional. So sort of just a reminder of what we talked about last time. But again, the whole point of this, again, is to show that we don't have any cases where you have A or alpha being true and then B or beta being false. So that entailment, that conditional still holds. So in logic, the entailment that we learned about in inferences and semantic relations and the conditional are very tightly related, and they can be used essentially as analogs to each other.
I have a question.
Yeah.
So it says A entails B if for every situation the truth value of A is equal to 1 and the truth value of B is equal to 1. So if we look at the truth table, the first row says the A truth value of A is equal to 1, but why do we need to know other situations as well?
Okay, so this says if alpha is 1, then beta is equal to 1. So I mean that's okay, so this okay, so yeah, so this is really the only row that we need to know, right? P and P arrow Q. We need to know that if this is true, then the other one's true.
Yes.
Yeah, so really that's just what we need to know. But I'm just saying that by default, because we have 0 as the antecedent for the rest of these, it just naturally comes out to be true. This is just a paraphrase that alpha arrow beta is a tautology. So there's like 2 ways you can check that. You can just check only the cases where this is true, but in a truth table, naturally the rest of those will just come out if you have 0 arrow whatever.
So if A arrow B is a tautology, then we don't need to think about the value of A being necessarily being 1.
I guess what I'm saying here is that if you check if alpha is true, then beta is true in a truth table, essentially you will get all of the information of alpha arrow beta being a tautology just by nature of the truth table.
Okay.
This definition up here is used more for, I won't write it down because people might write it down. This is used more for like formal natural deductive proofs where you just assume line by line that things are true. And then you say like P and P arrow Q is true, therefore P is true, therefore P arrow Q is true. And then you have things like modus ponens, therefore I know that Q is true. And then you have like this nice formal mathematical proof. The second one is really more for a truth table showing that the entire thing is a tautology. So both definitions work, but the second one, showing it's a tautology, fits more with a truth table. On the homework, though, on the fourth question, there's this word that I use that says jointly entails. And every semester I get questions about it. So I'm just going to cover it explicitly. Um, I'll still get questions about it, but just to make sure that I do cover it. Um, Sometimes you see things like P and Q jointly entails P and Q. And what this means is that you have two sentences in conjunction entailing something else. So it's like saying that I have a dog, or the fact that I have a dog and the fact that I have a cat entails that I have two animals. So, in order to set up something like this, uh, it could be written another way too. It could be like P, it could be Q, and three, it could be P and Q, something like this. So, to set this up, we take our jointly entails and we just put an and between everything. So, this would be saying that P and Q entails P and Q. So when we say two things or three things or four things jointly entail another, we just put ands between all of those individual things or all of those individual premises or individual hypotheses, whatever you want to call them. It's like saying fact one and fact two and fact three entail some other thing. The and is quite literally a logical and. So uh, as I get rid of all of these markings up here, and I put these ones back. When I use an and up here for P and P arrow Q entails Q, this easily could have been rewritten as P and P arrow Q jointly entail Q. That could have been written as that, and it has the same meaning. But instead of giving you one, it's sort of like taking two sentences and conjoining them into one. The first way I showed you, P and P arrow Q entails Q in the first line. That's like a conjunction in the sentence. While the second line that I just wrote, P and P arrow Q jointly entail Q. That's like saying two separate sentences entail Q. Okay, are there any questions about entailment here? Again, sort of the nice thing about this is that um, this is all stuff that you've already worked with the truth tables. It's just sort of taking the terms that we've already seen in the course and just like applying another layer to them, like taking them into another topic and seeing how they're used, like both in the linguistic side and now seeing them in the mathematical side. This course is really all about taking linguistics and sort of pulling it back and seeing the mathematical layers, which is both terrifying and exciting. And starting next week is when the excitement happens, when we actually get to see syntax and we get to peel back actual syntax and syntactic trees and see the math behind it. Which again is both terrifying and incredibly exciting. Okay, so there are some exercises on this, and what I'm going to do is I'm going to put the solutions on Canvas for these, just because these are just truth tables. It's just building truth tables and then assigning a word to the outcome of a truth table. So, um, yeah, there's really not too much going on other than just doing that. So I'm just going to put that up. The rest of the slides in this, I'll just talk about very briefly. Um, so we have logic laws and we have logical equivalence. We're not going to do this because we just did this with set theory and it's quite literally exactly the same. So there's no reason for us to do it twice. Um, what I do want to say though is that uh, there's no coincidence that logic and set theory are the same, because they both stem from the same system, which is called Boolean algebra. The difference between set theory and logic is that sets talk about membership, whether something is included in a set or not, and logic talks about truth. That's why sets are used for nouns and verbs and proper names and people and objects and things and relations. And logic is used for sentences and declarative statements and truth. So they're the same system, but they're just used for different things. They have different meanings. So the fact that the complement and negation, intersection and union and or, the universe and tautology are actually quite related when we think about truth. Truth is about being like one, like it's absolute truth. The universe is about everything. The empty set and contradiction are also very similar. They're used in the same way. Um, the subset and the conditional might not be as an obvious of a relation, but they're also quite tightly related to each other. Um, so we can take complex expressions and we can reduce them to truths using these laws, but we won't be doing that. Um, we can also actually take uh, all of the operators we have. So we have this system with and, or, if then, if and only, if not, and we even have exclusive or, but we don't actually need all of those. All that we really need in the system is the arrow and the contradiction symbol. That's all we actually need in our system. But as you can see, if we want to express something like P if and only if Q, we would have to write it as like if P then Q, then Q then P, then contradiction. And that just loses like all semblance of natural language. So in philosophy, that might be really nice for like mathematical proofs and proving that a system works and that it can do incredible things and that the syntax matches the semantics and the semantics matches the syntax. But for natural language and linguistics, this kind of thing isn't really convenient. So there's some neat things we can do in logic on the mathematical side and the theoretical side. But for us as linguists, like it's just not practical. So just some things that are there out of interest, but things that we won't be working with. Okay. So if you still have some mental energy left, I'd like to give you 6 minutes or so to work on these practice exercises from last time, translating English into logic, and then we'll go over the solutions and then we'll call it a class. So I'll give you 6 minutes or so and then I'll go over the solutions. If you have any questions or comments or anything, feel free to type them in chat and I'll respond. But I'll see you in 6 minutes otherwise. Okay. So I set up the keys in the top right. That way they don't take up too much of the screen. So first thing, all of the keys are positive. So although some of them have negations in them on the screen, the negations are not included in the keys. So if you just underline them and gave them letters, that's fine too. If you use different letters, that's fine. Um, I just use the letters that make sense to me. Okay, so the first one, if Addie learns to shuffle, she will be a great dancer. So I used A for Addie learns to shuffle, just because S I'm using for salmonella. So if Addie learns to shuffle, there's a hidden then here. So this might help you figure out where the arrow goes. So then she will be a great dancer. So if Addie learns to shuffle, then she will be a great dancer. So if A, then D. Or if you did shuffle for S, then if S, then D. Okay. B, Addie will be a great dancer, or she will not learn to shuffle. So the connective here is or. So Addie will be a great dancer. So here I've defined this as D. Or is the or connective, or she will not learn to shuffle. So here we have another connective, not. So shuffle in my case is A, it might be S to you, but then we put not. So for me, this is D or not A. To you, this might be D or not S. But remember, negations are connectives. So you should have a negation here. The key should be defined in the positive declarative. So whatever letters you use, it should be like X or not Y, D or not A, G or not S. Okay. For C, we have two negations. We have it is not the case that. So this is a negation. And then we have isn't, which is another negation. And then we have salmonella. So I shouldn't do isn't. I should really just highlight the int here. And then we have salmonella is dangerous to crabs. So here I have S. So this could be translated as not S. So I could just translate this as S if I want to, because not S is the same as S. So I guess I should put this in brackets. But if I want to be completely faithful to the English sentence, which is what I should be, I should just translate this as not S. That would be the best way to translate that because that is being completely faithful to the original sentence. Okay, D, this one's a little bit more complicated. Charles shows up if Elsa shows up, and the other way around. Uh, does anyone have any translations for this one?
I used the double arrow.
The double arrow. Yeah, that's one way to do it. So Charles shows up if Elsa shows up, and the other way around. So Elsa shows up, I used E. Charles shows up, I use C. Because it says if Elsa shows up and the other way around, you could use the biconditional here. So this is like saying Charles shows up if Elsa shows up and Elsa shows up if Charles shows up. So you could do that, or it would be perfectly okay to do if Elsa shows up, then Charles shows up, and if Charles shows up, then Elsa shows up. So you could do either way. And the other way around just means you flip the conditional. The left side is just an abbreviation of the right side. So the long way or the short way, either one is faithful to the original sentence. Okay, E is another one that's a little bit complicated. Actually, E is quite complicated. So let's just tackle the first part. If father and mother both go, then I won't. So how do we do this one? If father and mother both go, then I won't. So father goes. So if father goes and mother goes. So if F and M, then I won't. So I go is I, so then I say I won't, so not I. So I won't, that's negation, and, okay. So F and M, then not I. But is the same thing as and. So this says if only father goes, then I will go. So this part is a little bit more complicated. Um, so we might have to do some paraphrasing here to understand what this is actually saying. So what what's actually being said here? If only father goes, I will go. How should we translate this one?
If only father goes and mother doesn't go.
Yeah. So what we should do for this one is we should say if father goes and mother does not go. So if F and not M, then I go. So yeah, F and not M. Yeah. So even though there's nothing specifically said about mother not going here, because it says if only father goes, there is that entailment there. There's actually an entailment there that says that mother has to not go in this case for me to go. Yeah, but is a conjunction, since both sides need to be true in this case. This is like one condition: if mother and father both go, then I won't. But or and if only father goes, then I will go. So the left side is condition one, the right side is condition two. Yeah. So the right side is a little bit more, um, might be more difficult at first because there's some language that isn't explicitly there that has to be translated. And that's just with the word only. Okay. And the last one, there's nothing really complicated about the language in the last one. It's just that the language in the last sentence is it's just a lot of words. So I will take the train to school or the bus to school if and only if TransLink makes an effort to increase bus frequency and bus drivers' attitudes. So I don't have keys specified for this one, um, but I will take the train to school. Could be T, or the bus to school. So B, I'll take the train to school or I'll take the bus to school. If and only if, this is the biconditional arrow, translates, makes an effort to increase bus frequency. So that could be F, and bus driver attitudes, that could be A. So, um, train or bus, if and only if, frequency and attitude. So although F has a lot of words in it, the translation happened to be nice and direct. So that one, kind of nice, even though it had the most words. Was actually probably one of the least scary ones out of the final three. So
Can
were there any?
you switch
Sorry.
can you switch the placement of T and V and F and A?
Yeah,
Can you say F and A first?
yeah, that's fine. You can switch F and A with T and B, or with T or B, and you can also switch B and T inside the brackets too. Yeah, when you're translating these sentences too, you're also free to paraphrase them as long as the sentence that you are paraphrasing has the same meaning as the original sentence. So, yeah, in this course, you're free to translate the sentences however you want, as long as your translation has the same meaning as the original sentence. So, uh, yeah, that's something that you have to decide on your own to be careful with. So if you are paraphrasing something, you can email me and check with me first. Um, if you ever read a sentence too and you're not sure about the meaning of the sentence, or you have to double check, like, please ask me. Um, yeah, I try not to make the sentences too complicated on the assignments and the homework, but please double check if you need to double check. And if you do have logic experience, then of course you can. I should say, if you do have logic experience from like a philosophy course or a discrete math course, and you know different methods for truth tables or different methods for translation, you're free to use them. Just double check with me to make sure that they're consistent and correct. But like some of you might have learned truth tables where you don't do separate columns for everything and you just do a giant grid of ones and zeros. I know how to interpret that. So if you know how to do it, you're free to use it. Yes, if and only if is the biconditional. So if and only if is one direction, only if is the other direction. So if and only if is both ways. That's it for today. I should mention I have an announcement today, but there's no live lecture on Friday because I'm away. There'll be a pre-recorded video that I'll put an announcement out for. Um, it's one of the least intense lectures that we have. It's more talkative, very basic syntax. So it's uh, kind of convenient that it's the one lecture that I'm not here for because there won't be too many questions, hopefully. So I'll be back Tuesday. And as far as the grades for this test goes, uh, probably released tomorrow by the evening. So I'll release an answer key for that when the tests are out. So all the answers for all the question variants will be released when the test grades are out. If you have questions, you should, yeah, make a discussion post or email if you have questions. I'll still be able to answer email while I'm away if you do have questions. I just can't do Zoom meetings or do anything live, but I'll have my phone available so I can do email. So yeah, that is it for today. I'll see you next week. And well, I do have office hours tomorrow too. So if you have questions, I can see you in office hours. Enjoy the rest of your day and the rest of your week.